Okay, in this video, we are going to derive the formula for Newton's method. In the previous video, we just looked at graphically how this method works. We start with a certain point. You can call it x1 or x sub 0. Either way is fine. Just make sure you increase each time you find a new approximation. So if you're starting with x sub 1, you use that to make a tangent line to the function. And then you use that tangent line to find its root, x2 here. And x2 is going to be closer, if the method is working ideally, x2 is going to be closer to the root that you actually want. Then you use x2 to find a tangent line. Its root is x3. That gets you closer. And then you proceed as necessary. So we are going to create an equation of a tangent line in this formula derivation here, because you can see we're going to need quite a few tangent lines to do this process. So we're going to start with our initial guess, the point x1 comma f of x1, and we're going to create that first tangent line, the one shown in orange up here. That equation of the tangent line, this time around, we're going to write it in point slope form. All right. So point slope form, that's the one we use a little less often in this class. It's y minus y1 equals m times x minus x1 for the point x1 comma y1. Okay. So here we're given our point x1 comma f of x1. So let's put that in here. The point is x1 comma f of x1. And we actually know the slope of that tangent line as well. Okay, so we'll have all we need for point slope form. So at x1, f of x1, the slope of that tangent line, what's it going to be? Can you think of it? If you're watching this later on YouTube, how do we get the slope of a tangent line? We use the derivative. Yes. So the slope of that tangent line is going to be the derivative. So m equals f prime of x1. Okay. Now we can set up the basic equation for our line. We would say y minus y1, that would be our f of x1 value right here. So y minus f of x1 equals m times x minus, oops, we know what m is. Let's put that in. Okay, m is f prime of x1. Stick that in there. And then times x minus x1. Okay, so there's our nice point slope form of a line. So if you were to add f of x1 to both sides of the equation, get this thing solved for y, that would look like this. Y equals f of x1 plus f prime of x1 times x minus x1. And that might look a little familiar because this is basically a linearization of the function. Okay, so we've linearized this function's behavior. We can use a tangent line to approximate what that function is doing. So the value y here is going to be quite close to the value of the actual function. Remember how if we get close to that point, the tangent line values are close to the actual function values because there's very little difference between the y values near our point of approximation there. Okay, so this is a linearization of the function. We've created a tangent line. And we want to find the root given by that first tangent line because that's going to give us our x2 value to move us closer to the root that we want. Okay, so the root of this line that we've just created is at the point x2 comma 0. Okay, because it is a root, the y value needs to be 0. Okay. So we could say that y is 0. All right, y is 0. The x value is x2. So based on our line here, we would have 0 equals f of x1 plus f prime of x1 times x minus x1, which x in this case is the x2 point. Okay, so x2 minus x1. I'll make a little note that we were bringing this down to use. Okay. All right, so that is putting in the values of x and y, x2 comma 0, that satisfy this linear equation there. And in order to find the location of our root x2, we're going to solve this equation that we've just set up here. So let's solve to find x sub 2. Okay, which is going to be the root of that tangent line. So let's do this. 0 equals f of x1 plus, let's do some distribution here. Distribute that f prime of x1. So f prime of x1 times x2 minus f prime of x1 times x1. Okay. And now let's get x2 to one side of the equation. All right. Let's see. I guess, what am I going to do here? I'll move this over by subtracting. So negative f prime of x1 times x2 would equal f of x1 minus f prime of x1 times x1. Okay, make sure to keep track of your 2's and 1's there. Makes a big difference. Okay, and then to get x2 by itself, let's divide by negative f prime of x1. Divide negative f prime of x1. Okay, and so when we do that, remember you do need to divide both terms in the numerator. Common mistake that people are prone to making. But you'd get x2 by itself, and then you would have negative f of x1 over f prime of x1. Negative because of that negative right there. And then for the second term, the f prime of x1s would cancel out, and we would just have plus x1. Okay, now let's get this in a slightly more attractive format. I'm just going to put the x1 in front and say x2 equals x1 minus f of x1 over f prime of x1. Okay, so that's where the root x2 is. Okay, so we've found this value right here. So we've used our initial guess x1 to move closer to the root that we really want by finding the root x2. Okay, and so this value x2 becomes our new guess for the root that we're looking for. x2 is our new guess for the root of f of x. And then we're going to do this exact same process over again. So it's like x2 is the new x1. It's our guess now. We're starting here. We're going to create another tangent line. It's the one shown in green in the picture. So we create that new tangent line, and we're going to find the root of that tangent line, x sub 3. But you would do the exact same process all over again. You would say, okay, the point now is x2 comma f of x2. The slope is m equals f prime of x2. You do the exact same operations, so we won't do it again. We'll save some time here. But we're just going to keep repeating the process. You would end up with the same type of expression here, just for x3 instead of x2, and all the x1s would be x2s now. Okay, so we can keep repeating the process until we get as close as we need to the actual root. And we'll see with some examples here how you can tell that you're getting close, or how to see if you're as close as you need to be. But the next step would look like this. You'd find x3 by doing x2 minus f of x2 over f prime of x2. Okay, that would get you that x3 root. And then let's say that you found x3 and you still wanted to get even closer to that root there. Remember that you can do this again. There's a blue tangent line drawn in there that on this picture looks like it gets us very, very close. That would be x4 that you're finding with that blue tangent line, finding the root of it. So you do the same process again, just with x3 instead of x2, and you're finding x4. So that'd be x3 minus f of x3 over f prime x3. And then you could do that process again and again and again. You just move that subscript, it's called the index, up by 1 each time. So in general, we can come up with a formula for this. Your new x value that you're finding, your new approximation, is going to be the old approximation minus f of the old x value over f prime of the old x value. Okay, and so that is the formula for Newton's method, written in one way at least. All right, so this is a great idea to know for this section. Now, you could write this in another way that's a little bit more formulaic, a little bit more mathematical. If you say that the old x is x sub n, so you've found the nth approximation to your root. And then the new x that you're going to be finding is the next iteration. So you're trying to move that index n up by 1. So the new x is going to be x sub n plus 1. Okay, then you could write the formula like this. X sub n plus 1 equals x sub n minus f of x sub n over f prime of x sub n. So it's the exact same formula, just written in a different way. Since we don't always use words on our little subscripts in math here. So these two formulas, these are both ways of writing Newton's method. Now, this lower version, I'd say, is the more mathematically common one. The top version just makes it a little more intuitive. But formulas like this actually come up a fair amount, especially in computer science, because computer programming is particularly well suited to taking a previous value or taking one value and then running the same process over and over and over again. I mean, computers are great at that. So you'll often see things like this coded up so that we can run this process over and over again. Formulas like this are called recursive formulas. So a recursion is something that depends on a previous value. Or you'll also see these called iterative formulas. So a new iteration is when you're finding a new value based on the previous values. Okay, so this is recursive or iterative formula. All right. So in the next video, we'll get a little quick note, and then in subsequent videos, we will look at some examples.